Okay, so today we are going to look at our very last gas law, and it's known as the ideal gas law. So the first little bit of notes here is just going to talk about what an ideal gas actually is. So basically an ideal gas just has characteristics described by the kinetic molecular theory, which we learned a little bit about in the properties of matter unit. So when we're talking about a gas, when gas particles collide with one another, the collisions are elastic. That just means that they come into the collision and out of the collision with the same amount of energy. They don't actually lose energy when they collide. There are essentially no attractive forces between particles. So they do exist, but let's just put here, they're extremely weak. Okay, and the reason they're so weak and basically non-existent is because those gas particles are spread so far away from one another that they don't attract at all. The distances between gas particles are so large, they're so far apart, that the volume of particles in the gas can be assumed to be zero. Okay, so these are kind of the conditions which describe an ideal gas. So it's just good to know that, considering our law is known as the ideal gas law. So an ideal gas, in other words, kind of fits this description perfectly. It's a perfect gas. However, in reality, real gases are not truly ideal. They may break one of the rules listed above. The molecules will have to have some volume. Okay, at extremely low temperatures, they would have some force of attraction between molecules because the molecules are much closer together at low temperatures. So it would be significant. But the equations we've been working with, so Charles' law, Boyle's law, the combined gas law, all the gas laws we've been using work well for gases in ordinary conditions. That means like the temperature isn't extreme, the pressure isn't extreme. We're fairly close to that, not necessarily standard temperature and pressure, but we don't have like really extreme values for those. So in very ordinary conditions, gases are pretty close to being ideal. Okay, so let's just review the combined gas law. So we learned in our last lesson that the combined gas law is P1V1 over T1 is equal to P2V2 over T2. So this combined gas law allowed us to look at pressure, volume, and temperature all at the same time. And while doing that, we assume that the number of moles, or the amount of gas, is constant. Okay, so this just means that pressure times volume divided by temperature is equal to a constant. That's why we're able to set one set of pressure, volume, and temperature values equal to another set. Okay, so let's use that to kind of get to our ideal gas law. So if we are now going to allow the fourth variable to enter in, so we've looked at pressure, volume, and temperature, but if we went back to our first set of notes from the unit, we identified 4 ways of measuring gas: pressure, volume, temperature, and N. N represents the number of moles. So that would be the amount of gas. So the ideal gas law will allow us to look at all 4 of those things at the same time. So pressure, volume, and temperature we know are in a relationship like this: pressure times volume divided by temperature. If we're to add in the amount of gas, it fits in on the bottom of the fraction here. Okay, so that means that it has an inverse relationship with temperature, and a direct relationship with volume and pressure. This R value here, R is a constant, and it's known as, in this sentence here, it says where R is a proportionality constant called, there's two called the ideal gas constant. Okay, so we're going to talk a little bit more about that in a second. And N is the number of moles in the gas sample. So we come up with the formula like this based on the combined gas law, but it's usually written like this. Okay, I'm just going to cross those out. So this is typically how you would see the ideal gas law. PV equals nRT. Okay, so what do we do with this? So the equations above are known as the ideal gas law. Okay, so first of all, we need to talk a little bit more about this R value. Okay, so R, in order to solve a problem with the ideal gas law, you need to know what R is equal to. And because it's a constant, it always has the same value. So I'm just going to show you how we come up with this value of R. And we're going to calculate R based on the fact that at STP, standard temperature and pressure, gas has a temperature of 273 Kelvin and a pressure of 1 atmosphere. And we also know that 1 mole of a gas at STP has a volume of 22.4 liters. We know that from our stoichiometry unit. So what we can do is we can take this PV equals nRT, and we can use these standard temperature and pressure conditions to solve for R. Okay, so I'm going to rearrange this formula to isolate R. So to do that, I'm going to divide by N and T on this side, and I'm going to do the same on this side. Okay, so that gets rid of N and T there, and then I get R is equal to PV over NT. Okay, so let's plug in all these values and find out what R is equal to. So R is equal to a pressure of 1 atmosphere times a volume of 22.4 liters over 1 mole times 273 Kelvin. Okay, so if I multiply and then divide, I get that R is equal to 0.0821, and my unit here is atmosphere times liter divided by moles times Kelvin. So kind of a really messy looking unit. And this, I'm just going to fix this down here. Those should be dots for multiply. Okay, so we're always going to use this value for R. However, because we're using this value for R and we calculated it based on these units, atmospheres, liters, moles, and Kelvin, that means that when we use this value in a question, we have to make sure our pressures in atmospheres, our volumes in liters, and our temperature is in Kelvin. Okay, so that's just what is being described here. Okay, so the first step is to convert pressure to atmospheres, temperature to Kelvin, and volume to liters. Okay, so every other law, the only thing we had to worry about was the temperature, but in this law, everything has to be in a specific unit. So we need atmospheres, Kelvin, and liters. If we're given the mass of the gas, we have to convert it to moles. I'm just going to erase that. That's not how we do. We use dimensional analysis. And then we substitute into the equation and solve for the unknown. So let's just try a question and see how it goes. What volume will 15 grams of carbon monoxide gas occupy at 25 degrees Celsius and a pressure of 0.98 atmospheres? Calculate the moles of gas first. Okay, so why don't we do that first? Calculate the moles of gas. So we have 15 grams of carbon monoxide, and we want to know how many moles that is. So we're going to put grams on the bottom, moles on the top, and in 1 mole, how many grams do we have? Well, this is our molar mass. So we look at the periodic table, 16 for oxygen and 12.01 for carbon. So if we add those together, you get 28.01. Okay, grams cancel, and you're just dividing here. So you end up getting 0.5355 moles. So I've kept lots of decimal places here, and I'll reduce my decimal places later. All right, so let's now fill in what we know. Okay, we always know that R always has the same value, 0.821. Okay, number of moles we just calculated, 0.5355. Okay, the volume is what we're being asked, so that's our question mark. Pressure is 0.98 atmospheres, and the temperature is 25 degrees Celsius. So if we add 273 to that to get it into Kelvin, that's 298 Kelvin. Okay, so let's write out our formula. PV equals nRT. So you can either plug in first or rearrange first, whichever you prefer. If you were to rearrange first, you're solving for volume, so you just divide by pressure on both sides. Okay, if you want to plug in first, then you would go 0.98 times V equals 0.5355 times 0.0821 times 298. Okay, to get V by itself, I'm going to divide by this value here on both sides. And then I just multiply and divide to get 13.37, and my volume will always be in liters, and that's simply because of this R value here. It was calculated using Kelvin, atmosphere, liters, and moles. So liters has to be my unit for volume. Okay, let's try another one. So how many moles of gas at 100 degrees Celsius does it take to fill a 1 liter flask to a pressure of 1.5? Okay, so I'm just going to put my values here, PV, nRT. Okay, so pressure is 1.5. It's in the correct unit. Volume, 1 liter, correct unit. How many moles is what I'm looking for. R is always the same. And temperature, it's in degrees Celsius. So if I add 273, I get 373. Okay, so let's do our calculation. PV equals nRT. So this time I'll show you if you were to rearrange first instead of plugging in, just for those who prefer it that way. So if I'm solving for n, to get n by itself, I just divide by R and T. Okay, so then n is equal to PV over RT. Okay, so once our equation's rearranged properly, then we just have to plug in what we know. So we know that P is 1.5, V is 1, R is always the 0.0821. This value you don't have to memorize. I would always give you this value on a test or quiz. And 373 for temperature. Okay, so if I just calculate that, I get 0.049 moles. Okay, let's try another one. What is the volume occupied by 9.45 grams of acetylene gas, which is C2H2 at STP? Okay, so right away, as soon as you see grams, you know there's no grams in your equation. So you have to convert from grams to moles before you can do anything. So let's do that first, and then we'll identify our variables. So we're going to divide by grams, put moles on the top. In 1 mole, so it's C2H2, so 2 times 12.01 plus 2 times 1.01. So that would be 26.04. Grams will cancel, and you'll get 0.3629 moles. So if we make our values here, PV, nRT, pressure is, okay, so at STP, pressure is 1 atm and temperature is 273 Kelvin. Okay, so we've got 1 atmosphere. Volume's what we're looking for. Number of moles we just calculated. R is always the same. And T is 273. Okay, so this time I won't rearrange. I'll just plug in as it is. That way you can choose which method you prefer. So we've got 1. We don't know volume, so we'll leave it as a V. Here's our number of moles, our R value, and our temperature. Okay, so this I'm just going to divide by 1, which essentially does nothing. Okay, and V is equal to basically these 3 values multiplied together, which equals 8.13 liters. All right. Okay, this part here, I'm just going to do this. This is another way you can solve for number of moles, but we always do the dimensional analysis method, so we're just going to stick with it. So just cross that section out. All right, so let's do these last 2, and then you should be good to go to try some on your own. What is the mass? Okay, so mass, let's always think grams of a 750 milliliter of acetylene, okay, which was the C2H2 from the last question at STP. Okay, so right away we know if we're looking for grams, we're going to have to find moles using the ideal gas law, and then once we know moles, then we can convert to grams. So let's make our list here. PV, nRT, STP, so we know standard pressure is 1. Okay, notice volume here is in milliliters. So to convert milliliters to liters, you divide by 1,000. So that would make this 0.75 liters. N is what we're going to have to find. R is always the same. And T at STP is 273. Okay, and again, you'll always be given standard temperature and pressure as well, so that you don't need to memorize them. So let's use our formula. We've got 1 times 0.75 equals N times our R value times 273. Okay, so to solve for N, you need to divide by these two values. Whatever you do to one side, you do to the other. Okay, so these guys would cancel, and N would be equal to, we just calculate this, and it equals 0.0335 moles. Okay, the question's asking for mass, however, so we simply take our number of moles and we convert to grams. Okay, so in 1 mole, how many grams? Well, we're still dealing with acetylene, which was from the previous question, and we found its molar mass to be 26.04. So we're going to multiply, and we'll get 0.872 grams. All right, so this is just sort of like an extension question. What's the density for the gas in the previous question? Okay, and it's telling you it wants the density in grams per liter. So density then, if it's being measured in grams per liter, density is mass divided by volume. Okay, so we know that the mass is 0.872 grams, and we know that the volume was 0.750 liters. So that equals a density of 1.16 grams per liter. Okay, so just an extension question that you can do with the same information. Okay, so you can work on worksheet 6. This is the last worksheet other than the review, and I will put the answer key up today for that so that you can check it as you go.